So we're continuing our discussion of constructibility. And so recall, we saw that a number alpha is constructible, so this is some real number alpha is constructible precisely when you can obtain alpha by doing some combination of addition, subtraction, multiplication, division, and square roots from the unit. So from 1, or more generally, we'll just say from the rationals, because you can immediately get the rationals from just addition, multiplication, division of 1. Okay. One thing I want to point out is these first 4 operations, well, addition and multiplication are field operations, and subtraction is just the inverse of addition, and division is just the inverse of multiplication. So really these are just your field operations. Like within any field, you know your field will be closed under these 4 operations. So you take things in the rationals, the field of rationals, you perform these 4 operations, you're still in the field of rationals. So the first 4 aren't doing anything, right? But what the square root does is it has the potential to expand your field. So we saw last time that we can introduce a new field by starting out with Q, but then adding something that involves square root. So we looked at in particular the square root of root 2. So this is the field of rationals extended by root 2. There's more things in there than just in the field of rationals. The field of rationals is a subfield of this, but this is bigger. We said things in here, elements in this field, have the form some rational plus some other rational times the square root of 2, where P and Q are rationals. Yeah? Okay. And what we convince ourselves is that things of this form are closed under the field operations. So you take 2 things of that form, you add them together, it's still of that form. You find the multiplicative inverse, it's still of that form. That took a little bit of thought, but it's still of that form. Some rational plus another rational times the square root of 2. Okay, so that's what things inside of Q square root 2 look like. And now that we know what things look like, we can say what kind of stuff is not in there. So for example, I claim that the square root of 3 is not in Q extended by the square root of 2. It's not in there. There's no way to get the square root of 3 with just rational numbers and square root of 2's multiplied together, added times, divided together. There's no way to do it. And so how can we show this? Well, proof. Well, suppose he were in there. If the square root of 3 were in Q extended by the square root of 2, then it would have to be of the form the square root of 3 is equal to some rational plus some other rational times the square root of 2 for some P and Q rational. Okay, what should we do now? Well, yeah, let's just do some algebra, right? Let's square both sides. So that would give you that 3 is this guy on the right squared. But that's just P squared plus this second P squared, which is 2Q squared, plus this 2 times the first times the second, 2PQ root 2. So that's what 3 is equal to. But then I can solve for root 2, and I would get that my root 2 is just 3 minus my P squared plus 2Q squared divided by 2PQ. Why can I divide by 2pq? Well, you should check really fast. If p is 0, then you would have that root 3 is q root 2, and you would have to quickly check that that would be a contradiction, right? If my p is 0, it would be something of this form. But then if I square both sides, I get that 3 is 2 times q squared, which would mean 3 is even, which is a contradiction. So I couldn't have had p being 0, and I can't have q being 0, because if q is 0, I would have the square root of 3 is rational, but you know the square root of 3 is not rational. Okay, you can give a proof for it, just like the square root of 2 not being rational. So you can quickly do a little argument over here to convince yourself that you have to have p and q both non-zero. Okay, so that's a little argument on the side. But once you have that, then you can divide by your 2pq. And now you have the square root of 2 is, well, this is just a rational number. This is just a rational number. So the quotients of those rational numbers will be a rational number. So you get the square root of 2 is itself a rational number, which is a contradiction. You know the square root of 2 is irrational. Okay, so we know the square root of 3 is not in there. And similarly, you could show other things not in there too. Like you can convince yourself that a similar argument would work to show like the square root of 5 is not in there. Right? Like it's a different kind of animal. You can't get the square root of 3 or the square root of 5 from just using rational numbers than the square root of 2. Somehow the number 3, square root of 3 is like fundamentally different than the square root of 2 in terms of the rationals. And so we're going to come back to that in a second. But first I want to briefly remind you about what a vector space is. So in linear algebra, you learn about like vectors, right? And you have these vectors, and so you have some vectors, some v1, v2, etc. And in a vector space, what can you do with your vectors? Yeah, you'll be able to add them. So you should be able to add vectors. So you should be able to make sense of like what is v1 plus v2. And that should be something else in your vector space. So if this vector space is big V, then v1 plus v2 should still be inside of big V, right? And you should also be able to multiply, not a vector by a vector, although you do build up an idea of like a cross product. But the more simple notion of multiplying is just multiplying by a scalar. You should be able to multiply by some scalar. And so this is some value like a times your vector should still be inside your vector space. So what is your scalar? Well, your v here is a vector, your v here is a vector, but what is this a? What kind of creature is a? In linear algebra, your a is a real number, right? But in general, a can be anything that lives in some field. So in general, you can think about vector spaces as being over some field f. So
generally we use the real numbers, but you could think about vector spaces over the rational numbers if you wanted to, or vector spaces over like z mod 3z, whatever field you're interested in. So if that's confusing, just let real numbers be your field, but in general I'm just saying it could be other fields too, like rational numbers. And so what you're doing is you're taking some element of a field, you multiply by some vector, and it should still be in your vector space. And then this gives you the idea of a basis for a vector space. So what does it mean for a vector space to have a basis? Well, if your basis is some vectors like v1 through vn, then that means that any vector in your vector space can be written as v is some linear combination of v1 through vn. Some scalar alpha a1 times v1 plus through some scalar an times vn, where all of your scalars are in whatever your field is, like in the real numbers. So the classic example of this is like if you're in R2, you would say that R2 is a vector space. This is a vector space over the field of real numbers.
And so what is a basis for R2?
What are two vectors that you can build up everything to R2 out of?
1, 0, 0, 1.
Yeah, you could have one of your basis elements be the vector 1, 0, and you have the other basis element be the vector 0, 1. Sometimes you see this as E1 and E2. I'll just call it V1 and V2 to be consistent with my notation above. And then any vector in R2, if you have any vector x, so this is any vector v, some vector of the form, v1, some vector of the form, we'll call it x1, y1, can be written as a linear combination of v1 and v2. This is x, this is just called x and y. X copies of v1 plus y copies of v2, right? So anything can be written as a combination of v1s and v2s. You guys remember this from linear algebra? This is familiar. And then we do one more thing with our basis, is we insist that these vectors we pick are linearly independent. Linearly independent. And so what is that saying? That's saying like you didn't pick too many vectors to begin with. If you had also picked like a v3 to be in your basis, some v3, which is like 1, 1, you're like, well, these aren't linearly independent because you can build one out of the other ones. So v3 shouldn't be included in there. You didn't need it. You have too many. All you really need are the v1 and v2. And then once you settle on any given basis, you can show in linear algebra that all your bases have the same number of vectors. So you could have picked a different basis, but it would still have two vectors in it. And we call that the dimension of the vector space, right? So R2 is a two-dimensional vector space over R. Because any element in R2 can be written as a linear combination, so real valued multiples of these two vectors. There's like 2 degrees of freedom for R2. Okay. Why am I talking about vector spaces? We're talking about fields, not vector spaces. But if we come back and we think about this field, Q extended by the square root of 2, like what is it? We set things in here are of the form P plus Q square roots of 2. And so you could think that that's like a vector. These things are like vectors, P, Q. Where the top value is the value that's independent, that doesn't have a root 2 next to it. It's like a p times 1. That's like your 1 value. And the other value is whatever the scalar is that's being multiplied by the root 2. Right? So things inside of Q you can think of as vectors. And so you can think of Q root 2, Q extended by root 2, you can think of as really being a two-dimensional vector field over Q. And so I'm going to introduce some notation here to summarize this. I'll say the degree of Q root 2 over Q is 2. That's just saying you can think of Q root 2 as being a degree 2, a two-dimensional vector field over Q. So what is the basis? What is the basis for this vector field? The basis should correspond to like 1, 0, and 0, 1. And so in this case, you can think of your bases as being elements of the form 1 plus 0 root 2 and 0 plus 1 root 2. And convince yourself anything is just a combination of this. P plus Q root 2 is just P copies of the first guy plus Q copies of the second guy. Yeah. This is just a vector. This is just a vector space over the field Q. Okay, good question. Sorry, my bad. Okay. Good. I said the cube root of 3, the square root of 3, is not inside of Q extended by root 2.
So what I want to do now is say, well, if the square root of 3 is not in there, what happens if we throw him in? So we had that q was sitting inside of q square root of 2. What I want to do now is look at q extend by the square root of 2, but then also extend it by the square root of 3. So what do I mean by this? I mean the smallest field that has q, all the rationals as a subfield, that also has the square root of 2 and also has the square root of 3. But then necessarily also has all combinations of those things. So let's spend a few minutes thinking about what does this look like? What do elements in Q extend root 2, extend root 3 look like? So name some elements in there. Well, certainly like, all the rationals are in there. And we know like the square root of 2 has to be in there and the square root of 3. But what else has to be in there? Yeah, well, anything you can get from like rationals plus rational combinations of 2, or rationals plus rational combinations of square root of 3, or you might say rationals plus rational combination square root of 2 plus rational combinations p, q, r, rational combination square root of 3. But now you point out there's another kind of creature in there too, right? And that's the square root of 6. The square root of 6 is in there. And just like we argued before, saying that the square root of 3 isn't secretly some combination of things with square root of 2, square root of 3 is not inside q extended by square root of 2, you can argue the square root of 6 isn't secretly something of this form. You can say, suppose square root of 6 is equal to something of this form, square both sides, you can work your way at it and get a contradiction, right? So square root of 6 is another fundamentally different kind of creature. And so here's one possibility. Maybe that's it. Maybe things in this field just are things of this form. I mean, are there anything else in there that's like fundamentally different? It's like, you did square root of 2 times square root of 3. That gave you square root of 6. What if you do square root of 2 times the square root of 6? Would that give you something else? Yeah, if you just do square root of 2 times square root of 6, what does that give you? Yeah, it's like this is the square root of 2 times the square root of 2 times the square root of 3. So that's just 2 square roots of 3. So okay, that's nothing new. And similarly, if you did do square root of 3 times the square root of 6, what do you get out? Well, that's just going to be a 3 times the square root of 2. So that seems like that's everything. So we should probably take a couple of minutes to convince ourselves, though, that elements of this form really are closed under field operations, right? Okay, well, if you take two elements of this form and you add them together, it's clearly still of this form. You just add the respective coefficients. What if you multiply them together? Well, I think this kind of argument here already suggests you'll end up with something that just has the square roots of 3, square roots of 2s, and square roots of 6. If you want to see it out, we can do it really fast. So suppose you have two elements of the form, so let's call them, I don't know, p plus q root 2 plus r root 3 plus s root 6. And let's just multiply that by, let's call it a plus b root 2 plus c root 3 plus d root 6. And check what you get. P and q, p and a is just pa plus, well, you can do p times all those things, right? And when you do p times all those things, you just get things with root 2, root 3, and root 6. Plus pb root 2 plus pc root 3 plus pd root 6. Great. Then you do q root 2 times all that stuff. So what do you get? Well, you get something with the root 2 for the first guy, and then when you do q root 2 times the second guy, the root 2's cancel, so it's just 2
BQ, and then so that's just something of the first form, just a rational, plus times the third guy, you just get a root 6, you get CQ root 6, plus times the next guy, you just get, well, we just said root 2 times root 6 is going to be 2 root 3, so I get DQ with a 2 root 3, okay, and so forth and so on, right? And then you add the respective pieces, so you end up like in front of you, square root of 2, you would have like PB plus AQ plus so forth and so forth, square root of 2, and so on. Okay, so I think it's pretty clear that's closed under multiplication. This doesn't take too much work to convince yourself of. What perhaps is more subtle is why is it closed under division? In particular, we should convince ourselves that the multiplicative inverse of something of this form, that 1 over P plus Q root 2 plus R root 3 plus S root 6, now this is secretly something of this form, something plus something root 2 plus something root 3 plus something root 6, where all those coefficients are rational. So how do we know that? Well, we're going to have to do something very similar to the Q extended by root 2, where we need to multiply it by something that works as a type of conjugate, right? So what's a good candidate? What should we multiply it by? There's probably a few different ways to do this. Let's just group this into two parts and change that plus to a minus. So we'll make this P plus Q root 2 minus R root 3 plus S root 6. And we'll multiply the top by the same thing. Let's see what we get. So on top, we just get this expression, P plus Q root 2 minus R root 3 plus S root 6. On bottom, the first piece squared is going to be P squared plus 2Q squared plus 2PQ root 2. That's my first piece. Minus the second piece squared is going to be 3R squared plus 6S squared plus what? 2 times RS times root 3 times root 6. Root 3 times root 6 is 3 root 2, so you end up with 6RS root 2. Right? But this bottom then is just of the form rational plus rational root 2. And we know that rational plus rational root 2, when you divide by it, is the same as multiplying by some rational plus rational root 2. Because we know the inverse of 1 over P plus Q root 2 is some rational plus rational root 2. So really it's just this top thing times, it's really just this top piece. Instead of dividing by all this, you're just timesing by some, A plus B root 2. But then you can show that when you multiply that out, it's still of the right form. So sure enough, you get that this is closed under multiplicative inverses. So in particular, every element of the field, every non-zero element of the field has a multiplicative inverse. Okay, great. A little bit more messy, but works exactly the same way as when we argued that Q extended by root 2, this collection of elements here, actually forms a field. So this collection of elements forms a field. So what can we say about this field? So let's think about it a little bit. We said that the degree of q extended by root 2 over q is 2. What do you think is the degree of q extended by root 2 and root 3 over q? What is the degree of this guy as a vector space over q? What's the degree of this as a vector space over q? Like, what are your basis elements? Yeah. Q root 2 root 3 thought of as a vector space over q just has the basis 1 root 2 root 3 root 6. Clearly, everything can be made as a linear combination of these. That's what we said right here. That's what this is saying. Everything is just a linear combination of 1, root 2, root 3, and root 6. And we've argued that they're independent. You can't get root 3 from 1s and root 2s. And you can argue similarly, you can't get root 6 from some combination of these other guys. Right? So they're a linearly independent collection of vectors that give you all elements in your space. And so we would say that this degree is degree 4. It's a degree 4 vector space, because it's a 4-dimensional vector space over Q. So if I think about Q extended by root 2 and root 3 over Q, it's degree 4. If I think about Q extended by root 2 over Q, it's degree 2. There's one more thing I might want to ask about. It's, can we make sense of this question for these last two guys? Can we instead think about Q extended by root 2 and root 3 as a vector space over not Q, but over Q root 2? So what do I mean by this? What I mean by this now is my scalars, whenever I have scalars, things like A and B, my scalars, whatever they are, will belong to Q root 2 instead of just being rationals. So now, what do elements look like? If my scalars, if I can multiply by not just rationals, but by things in Q root 2, what do elements look like? Before we had said elements were of the form some rational P plus some rational Q root 2 plus some rational R root 3 plus some rational S root 6. But root 6 is really just the same thing as root 2 times root 3. I'm going to reorganize that a little bit, because now I'm thinking about P plus Q root 2 all as just a single scalar. So I can think of this as just being P plus Q root 2 plus, here on the right, I'm going to factor out a root 3. R plus S root 2 times root 3. Notice all I have here now is some scalar A and some scalar B as elements of Q extended by root 2. And so I get everything is of the form A plus B root 3, where my scalars are allowed to be not just rationals, but rationals extended by root 2. So what is the degree of this extension? Well, the dimension of this as a vector space over Q root 2 would say this is a dimension 2. This is a dimension 2 vector space now. My basis elements are just 1 and 3.
my basis now is just 1 and 3. 1 and root 3, 1 and root 3. So this extension right here, we'd say it's a degree 2 extension. The degree of q extended by root 2 extended by root 3 over q extended by root 2 is just 2. Oh, hey, that's a great observation. So let me just write this down. So Lisa just pointed out that if I asked you what is q extended by root 2 extended by root 3 and extended by root 6, you would say, well, that root 6 isn't doing anything because you already get the root 6 from free from the first two. So this is the same as just q extended by root 2 and root 3, right? In a similar way as if I asked you what is q extended by the square root of 4, you would say, well, the square root of 4 is just 2, and you already had 2 in your rationals, so that's really just q. That didn't do any extra work at all, right? Yeah, it might take a little bit more thinking, but you should convince yourself also if I ask you what is q extended by like 1 plus the square root of 2, you should convince yourself that really is just q extended by the square root of 2. Because if you have 1 plus the square root of 2, and you have 1 in the rationals, you have to have the square root of 2. So he must be in here as well. But this guy's also in here, because if you have square root of 2 and you have 1 plus the square root of 2. So those are really the same thing. So sometimes, there's dumb ways you might think of writing, but this is kind of the simplest way to think about the extension. Yeah, okay, that's great. That's really good. Okay, so this result here is a special case of a more general result that I want to mention and try to sketch the proof of. In general, whenever you're extending vector spaces, whenever you're extending fields, so whenever you have some field, let's just say F, a subfield of, I don't like to use J, but I'll use J, a subfield of K. I guess, that's kind of a weird notation. Let me use E, a subfield of F, a subfield of K. Whenever I have these fields, if I calculate the degree of F over E, so this is asking what is the dimension of F as a vector space over E? How many basis elements do you need to write everything in F using just linear combinations of your basis with scalars in E? And you also calculate the degree of K over F. That will come out to be the degree of K over E. That's exactly what we had here. We extended by 2, we extended by 2, we end up with an extension of 4. So you extend by something that's degree 2, then you have another degree 2 extension, the result is 2 times 2, 4. So let's think about why this is the case. Okay. What does it mean to, well, let's let the degree of F over E, let's give it a name. Let's call it some value M. What does that mean? That means F has a basis alpha 1 through, maybe I shouldn't use alpha because that might confuse you. U1 through UM over E. So any element of F can be written F is equal to some scalar in E
times u1 plus some scalar in E times u2 and so forth through some scalar in E times um. Right, that's what it means to have a basis. You can write any element of the field as some linear combination of that basis, where here our coefficients, our E1 through EK, are elements of E. Similarly, let's give some name to the degree of K over F. Let's say that's N. Then that's saying that K has a basis. Some, we'll call it V1 through Vn, n elements, over F, over F. So that's saying that for any element of K, any K and K can be written, K is just some element of F times V1 plus some element of F times V2 through some element of F times Vn for some F1 through Fn being elements of F. Now what we want to think about is we want to try and figure out what is the degree of K over E. What is the degree of K over E? Can anyone think of a possible basis? Maybe we should go back to our example. In this example, what was the basis for this guy? Just 1 and the square root of 2, right? And then the basis for this guy was we said we just need 1 and the square root of 3. And then what's the basis for the q extended by root 2 and root 3 over q? We said we need 1, root 2, root 3, and root 6. But notice there's a relationship. Everything in the basis are just the combinations of things in these two basises. Yeah? 1 and 1 gives you 1, root 2 and 1 gives you root 2, 1 and root 3 gives you root 3, root 2 and root 3 gives you root 6. So it seems like maybe a basis should be all the ways of multiplying you use with your v's, like u1 times v1, u1 times v2, and so forth, and then u2 times v1, u2 times v2, and so forth, all the way until you get down to um times vn. Those mn elements. Well, why is that actually a basis? Let's check. Suppose I have some element k in the field K. I already know that I can write K above as just some F1 V1 plus some F2 V2 through Fn Vn. But what is F? My F's here are elements of big F. But I know that big F, elements of big F, can be written as a linear combination of these u1 through um's. So I can write big F1 as being some linear combination. I'll call it E11 u1 through E1m um. So I can write my F1 this way, and it's still times V1. And you can rewrite all of your F's as linear combinations of these U1 through UM's. So this last F is just going to be, we'll call it En1 U1 through Enm Um.
and that's times Vn. But then what do you get if you multiply this all out? You have some coefficient, E11, U1, V1. And then you keep going. You know, you get some coefficient like E1m times UM, V1. And so forth and so on, all the way until you get to the end, ENM times UM, Vn. That is, you just showed that any element of K can be written as a linear combination of these elements. Well, to check it's a basis, you should convince yourself it's linearly independent, but that'll just follow from the fact that your U's and your V's linearly independent. And so sure enough, there are mn elements in our basis, so this degree must just be m times n, the product of the two degrees. Okay. Why are we doing this? Well, let's go back here. We started out with the rationals, and now we have some understanding that when you add root 2, we can talk about what happens. And we have some understanding that then you can then add root 3, you can understand what happens. And what are you doing when you're constructing? You just keep adding more things with square roots, right? When you do addition, multiplication, subtraction, division, you stay within the field you're in. The only time you go to something big is when you add a square root. But now we understand each time you add a square root, you're just going to be going one step further. So maybe you'll add the square root of 5. Or maybe you'll add the square root of 2 plus the square root of 3 or something. You'll add one step further, and now we have some sense of understanding what that's doing overall. You know, if we just keep adding a square root each time, we'll see next time that's just adding something of degree 2. So overall, you always end up with something that's just a product of 2's. A degree 2 to the n extension of q. And that's going to tell us something about what kinds of numbers we can construct. So we'll continue with this next time.